right, welcome back. We're fortunate to have a nice discussion panel of several experts on measuring and fitting radial velocities and establishing the significance of their signals. For those of you who have been here all morning, you will have heard Jason Wright just give an overview of radial velocity planet fitting. Sharon Wang describe the standard methods for measuring radial velocities and their uncertainties. Hara from Geneva on the statistical significance of signals. And hopefully each of you has had the chance to watch on YouTube the power and limitations of Gaussian processes by Vinesh Maguire-Rajpaul from Cambridge University. Each of them will get a chance to give a brief either summary of their talk to help refresh our minds, or if there's some other maybe more meta points they wanted to make before we go into the question session. So I guess we'll start in order. Jason, would you like to give an overview or some extra philosophical discussion of your talk?
Yes, I would. And I'm not sure. I think I have failed to share my screen. I'm sorry. I'm going to try this one more time. Do that. Okay. I think that's working. You can tell me if not, Eric. Right. So my summary was simply how to fit the exoplanets, and I think we just heard a great talk on the complexities of periodograms and how you can construct different kinds and interpret them. One of the questions that came up a bunch was accuracy versus precision yesterday, and I did get to mention a bit of that nuance. One more thing I'd like to mention is that we haven't discussed barycentric corrections. And so I want to make sure everyone is clear on this because it's important. All of the radial velocities we measure for stars are very large. There are no stars for which we only measure these tiny little radial velocity variations. Typically, they vary between 20 and 30 kilometers a second over the course of the year. And that's because the Earth is orbiting the sun at 30 kilometers a second. And so when we move toward the star, we can measure a huge Doppler shift. So this whole game of EPRVs is not about measuring small shifts. It's about measuring very large shifts very precisely. In particular, we're trying to measure them to a part, well, we can already do things like a part in 10 to the 4, we're pushing toward a part in 10 to the 5, and ultimately, if we want confident detections of Earth-like planets, we're talking about measuring these large Doppler shifts to a part in 10 to the 6. So when you think about the cross-correlation method or the forward modeling method, when you think about where those spectral lines land on the detector, they're not moving by fractions of a pixel. They're moving by 10 pixels back and forth or something like that. And that's what we're trying to measure. Now, fortunately, we have an excellent model for that. Many groups have solved this problem many times. I've put up here my paper with Jason Eastman where we describe the calculation. But under the hood of all of the radial velocities you'll be playing with this week, we've already removed that signal so you don't have to worry about it anymore. There are some subtleties with binary systems, but for the most part, you can forget about it because the problem's been solved. So that's what I wanted to say. You're muted, Eric.
Great, thank you very much, Jason. Sharon, would you like to give an overview of your talk or any additional comments?
Yeah, sure. I'll give a quick summary. So I talked about standard methods for measuring RVs and their uncertainties. There are roughly 2 families of standard methods, that is using cross-correlation function or used for modeling. And then I touched on mostly the errors in measuring RVs, that is photon errors, CCF and forward modeling actually perform equally well to photon limited precision under idealized conditions. And also you can have errors in mask or template, which ideally only cause bias, but they could interact with the other 2 terms below and cause you trouble. That is spectral contamination, which includes solar contamination, telluric emission, telluric absorption. I talk about how we deal with these and sort of at what level they are operating and what's the best effort in mitigating them these days. And finally, some new non-standard methods in measuring RVs in the spirit of battling with stellar variation or stellar jitter to tease out the true Doppler shift caused by the planets instead of the intrinsic Doppler shift causing by various stellar astrophysical phenomena. And that was my talk. All right,
Thank you very
stop
much.
there. You're welcome.
Natan? You might be muted.
You just heard my talk, so I don't think I need to refresh any memories. Yeah, maybe something I'll comment on briefly. Can you see my screen?
Yes.
Okay. It has to do with the way you define the noise model, and I think it's something that might be helpful in practice is to see your noise model as a frequency filter. And here is an example from this paper where the true noise has a certain time scale defined here, and you assume another time scale. And so if the noise is in fact white, it's uncorrelated, but you think that it's correlated, and you look at the average periodogram you would get, you see that it completely depletes the power in low frequency regions. So and conversely, if there is power in the low frequency region because the noise is correlated, but you assume that it's not, then you will have on average a lot of power in the low frequencies. So be aware that when you define a certain noise model, it might filter out certain parts of your spectrum, and especially it might kill some of the planets. But I've seen situations where the noise model kills too many planets, I think. The correlation that is fitted to the data is too strong, and it filters out too much of the signal at low frequency. Yeah, that's the point I wanted to make.
That's a great point, something that I think is only recently being appreciated in the community. So thanks for raising that for everyone. And then Vinesh, since we didn't hear from you this morning, we're going to give you 10 minutes to sort of give an overview of your talk.
Okay, let me just share my screen. Are my slides visible?
Yes, they are.
Okay, great. Yeah, just before I start, thanks to the organizers for all their hard work putting this workshop together and for inviting me to speak. So GPs in 10 minutes or less, let's go. Very, very often in physics, almost by default, we work with so-called parametric models. Classic example of this is a mass on a spring. We know how to write down the equation of motion for the system, and when we solve that equation, we get a solution that depends on just two unknown parameters. If we now measure the position of this particular mass over time, we can figure out the values of the unknown parameters. And as Bayesians, we'd say we're computing the posterior distributions for these parameters. And these parameters will tell us everything we want to know about the system. Another example is a Keplerian orbit of a planet around a star. Solving the relevant equations of motion leads us again to a parametric expression for RVs versus time, with these 5 or 6 parameters determined by the properties of our planet and star, as we saw in Jason's talk. Okay, so that's pretty easy. But unfortunately, life is not always easy, and sometimes we don't know how to parameterize the physics we're dealing with. A good example of such a situation is provided by stellar variability. In this RV time series from a star called Kepler 78, most of the variability you see here is due to rotating active regions on the star. Even though there is some regularity and periodicity to the signal, the temporal and spatial randomness that comes from active regions appearing, then growing, hanging around while rotating, and eventually decaying means it's basically futile trying to write down a single parametric model that can capture all this possible behavior. Fortunately, though, all is not lost, and this is where GPs enter the picture. Now, this isn't a technical definition, but long story short, one way to think of GPs, of a GP is just as a really, really big and actually infinite dimensional Gaussian distribution. Okay, so a multivariate Gaussian distribution over just n random variables is specified by an n element mean vector and an n by n covariance matrix, which defines how the different random variables relate to each other. And samples from this distribution will be vectors. A GP extends this to a distribution specified by an infinitely long mean vector and an infinity by infinity covariance matrix. But instead of specifying infinitely many values, which would be hard, we instead specify mean and covariance functions that just provide recipes for computing any values we choose. And since you can think of a continuum of real numbers as an infinitely long vector, GPs actually define probability distributions over functions. The GP's mean function is usually not interesting and is often just set to 0. The covariance or kernel function, however, is really, really important, as this defines all the interesting properties of our GPs and the functions we can get out of it. So the most widely used covariance kernel in the RV context anyway is called the quasi-periodic covariance kernel, and it has just 3 hyperparameters. One sets an overall period for the functions, another defines the complexity or the shape of a function within a period, and a third defines how quickly functions evolve or move away from strict periodicity. And then by varying just those 3 hyperparameters, we can describe an enormous diversity of quasi-periodic functions, a few examples of which are plotted here. Some are strictly periodic, others are only approximately so. Some change shape slowly, others more rapidly. And some are quite simple, they look almost sinusoidal, while others are quite complicated with a lot of structure in a given period. So this quasi-periodic covariance kernel and the functions it describes turns out to be really useful for modeling quasi-periodic signals in general, but in particular stellar variability in RVs. But I should just say that many, many other covariance kernels do exist, which are useful for describing different types of signals. Anyway, so we said that GPs define probability distributions over functions. So if we're Bayesians, we could actually choose to use a GP as a prior distribution over functions. In other words, we might not be able to write down exactly the unknown function we want to model our data, but we could use a GP to specify some of the properties we think our function should have. It then turns out that thanks to the really remarkable and convenient properties of Gaussians, we can combine our GP prior with observed data to end up with a posterior distribution for our unknown function that we can compute analytically. Or in simple terms, it turns out that we can use GPs to learn unknown functions with error bars directly from our data. We're not learning the parameters of one fixed function, we're learning an unknown function from scratch. To illustrate this, here are some noisy observations I synthesized with a complicated parametric function, the details of which you can assume were lost when my computer crashed or something. Instead, all we are going to assume is that our data have some sort of periodic behavior. So I'll start with a GP prior on my unknown function with an appropriate covariance kernel, do a bit of linear algebra, and almost by magic, I end up with a function that looks remarkably similar to the true function I used to generate the data. And better still, I have error bars, which correspond to the standard deviation of the infinitely many functions that are actually compatible with my data and my prior. I can interpolate and extrapolate, I can do model comparison, all as though I were working with a parametric function. So in my pre-recorded talk, I discussed several exoplanet-flavored applications of GPs in some detail. The first was that they're great for modeling stellar activity jointly with planets, for example, in RVs. Doing so helps you avoid mistaking stellar variability for a genuine planet, and also leads to more accurate constraints on the properties of any real planets. GPs are also useful for studying periodic or quasi, hang on, these points aren't going in there. Anyway, they're extremely flexible and powerful, and I'll show you some applications now. The priors can usually be informed by physics, and they're fully probabilistic, which we could encapsulate by saying they know what they don't know. This is something which isn't true for a lot of machine learning algorithms, including neural networks, for example. They're easy to implement. You can code up GP regression from scratch in one sitting, and they're often a lot better than the practical alternatives. Okay, so onto the applications. Yeah, I already mentioned that they're useful for modeling stellar activity jointly with planets. They're useful for characterizing quasi-periodic phenomena like stellar rotation. They're useful for modeling some of the messy and unpredictable behavior of our observing instruments. And again, dealing with such systematics will generally give you a better chance of finding hard to detect exoplanets. I discussed also in my pre-recorded talk how GPs can be used to model stellar spectra themselves in order to extract RVs. And finally, I discussed how GPs give you a powerful way to take some real data full of noise and gaps and complicated nuisance signals we don't understand, and then make realistic synthetic data with properties that mirror the real data. And then finally, just to round out the picture, I also discussed some of their limitations. The first was that they can be computationally expensive and often are not ideal for large data sets. I noted that choosing a good covariance function is critical, and you have to be quite careful how you interpret and constrain the hyperparameters. Being as flexible, I might just go back quickly and say the reason they're called hyperparameters is that they govern the properties of entire distributions of functions, not just the parameters of one function. Okay, then being as flexible as they are, GPs can actually fit just about anything if you use them recklessly, but there are good ways to avoid such problems. And finally, great as they are, they're not always going to be the right tool for every job. Sharon described GPs in her pre-recorded talk as a powerful hammer. So if you have a powerful hammer, you just need to avoid the temptation to interpret every problem you encounter as a nail, because sometimes a screwdriver or something might be more appropriate. Okay, so that's my attempt at GPs in 10 minutes.
Very impressive. Thanks for that power overview. And of course, people are referred to the longer presentation on YouTube if they'd like to go review some of those equations a little bit more slowly and see more of them in detail. So now I'd like to switch over to the panel discussion portion. So I've been trying to go through the questions, and a lot of the good questions are being answered in the Q&A session. So I see some questions are a little bit redundant. So if you ask something and don't see someone answer it, it might be because they saw someone else had already answered it. So be sure to check the answer session. And I'll also point out there's several useful posters on the website that are related to today's session. And so some of those might be worth checking out for more details on some of the methods. So one thing I picked up on in the talks was a little bit of confusion over what we were doing with the GPs. I think there were some cases where we were modeling the velocities as a function of time, and some cases we were measuring the spectrum as a function of wavelength. And so I saw some of the questions people were asking things, and maybe you could comment on the computational cost for both of those and sort of how they compare.
So there are two very, very different applications. In the first case, we're modeling radial velocities that have already been extracted from a spectrum. So RVs as a function of time. And we're using the GP usually in that context to try to account for stellar variability that we don't really know how to parameterize. Now, typically, you don't have that many RV observations for a single star. If you're lucky, you might have, order of several hundred. So in cases like that, the GP computational bottleneck, this n-cubed scaling with a number of data points, isn't a big deal. You can do that kind of modeling probably on your laptop or desktop. When you're modeling stellar spectra themselves, so you don't yet have the RVs out, you want to model the entire spectrum, if you're dealing with like a HARPS or HARPS North spectrum, you might have about 400,000 fluxes versus wavelength. So then it does become a problem. So there are a few workarounds. One is don't use a GP. If you want to use a GP, which does have some advantages sometimes, then there are some very clever methods, some clever codes which can speed things up significantly and make GP regression tractable even when you have millions of data points. The first one that comes to mind is a package called Celerity by Dan Foreman, Mackey, and some of his collaborators. So I would recommend very strongly taking a look at packages like that. Another option is just breaking up your data into smaller chunks. And in the case of modeling stellar spectra, that might be a reasonable thing to do because well, you know, they already come in different shell orders, and you expect what's going on in one spectral line in the blue end to be completely unrelated to a different spectral line way down in the red end. And by doing that, you can make things more computationally tractable.
And does that introduce any systematics into RVs?
That's an interesting question. It's not one that it's not a problem that I've thought about very much. In the test that I did with kind of, you know, synthetic spectra, where I know what the true RV shift should be, I didn't find any evidence of there being like obvious systematic effects. But I guess, you know, since if you think about the barycentric shifting of lines in and out of a given order or whatever kind of wavelength range you're working with, you're going to lose information, but I don't really see how it would introduce systematic errors, because the you know, loss of overlap in between the different orders should be accounted for. But it's a good question. I think I do need to think about it a bit further.
Thanks. We had several questions about how various atmospheric effects, caloric absorption or differential extinction, might affect the velocities. And I think this probably comes to Sharon, because you mentioned that sort of everything was perfect. Well, then the CCF and the forward modeling would give you the same answer. But maybe if there's imperfection, your continuum model or your mask or something, then there could start to be differences. So could you maybe say something about to what extent the radial velocities you extract would depend upon variability in the atmospheric effects, and if that varies from method to method?
Yeah, sure. So the two methods are very different in one way, which is that in some cases, forward modeling uses convolution. So it starts with the spectra that are not convolved or not broadened by a spectrograph, and you convolve it in. And so this adds a mathematical complication, because very often we divide out the spectral contaminants in the spectrum. But mathematically, it is incorrect to divide something out after convolution. So mathematically, you have the stellar spectra, you multiply the, say, absorption contaminants, and then you convolve them over, mimicking the broadening process by the spectrograph. But if you just divide out from the convolved spectra, it's mathematically incorrect, because convolution does not distribute over multiplication. So that's actually, it sounds like a small subtle mathematical effect, but this actually turns out matters quite a lot when you deal with deep caloric lines in the near infrared. So that's one subtlety between the two methods. Otherwise, it's actually, those two methods actually don't differ by that much. So when convolution comes in, it complicates things a lot. But when you have a stabilized spectrograph, you're just modeling things, or doing CCF, the difference is really just whether you're stepping through the velocity space or you're using some sort of optimization algorithm. So forward modeling sometimes wins when you have those, you know, folded in contaminants.
Okay, so if that didn't get all the question, maybe you can submit another one, the follow-up to some of these as I sort of go through things. I'll try to go around. One interesting sort of contrast I heard was, I think Jason said, you can't trust periodograms. To the full quote, it went on to say you have to interrogate them. And I believe Vinesh said it's not magic. Okay, so maybe that was in his longer talk before. And so trying to understand sort of what the strengths and limitations are. And this connects to one of the questions in the Q&A, which was, I think a lot of people are using periodograms to mean a lot of different things. And so maybe people could go through and talk about some of the different variations of periodograms that they use, and why they make those choices, and if there are certain caveats with some choices. So I don't know, maybe Jason, do you want to get started with some of the ones you've used and the caveats you'd want to place on them?
Sure. So the periodogram I was referring to is sometimes called the Lohm-Scargel periodogram. And it really is just picking all of the trial frequencies you're interested in and looking at the amplitude of the best fit sinusoid at each of those periods. And so when I said you can't trust them, there's a few reasons. If you have a highly eccentric planet, then its power is actually going to be distributed at harmonics. So right away, you've got power where it doesn't belong. Aliasing, just the non-uniform sampling of that curve, is going to take some of that power and put it other places. And as we heard on the first day, especially long period power is going to love to show up at your observing cadence. At one day, if you only get to observe during full moon, it'll show up at the lunar cycle. And since you can only typically observe for part of the year, it'll show up at 1 year as well. And so that particular periodogram is very powerful heuristically and to explore your data, but you can't trust it. Now, there are lots of other much fancier forms where you've done all sorts of things, as we've just heard in these other talks, and those weren't the ones I was talking about. And I'd say if you understand them and their limitations very well, then absolutely you can powerfully use them to, for instance, assign a false alarm probability.
Natan, would you like to maybe expand on that and some of the different types of periodograms you're using?
Yes, sure. I think I'll build up on what Jason said about the fact that it's hard to find eccentric planets, for example. I think that there are like 3 main difficulties in RVs. It's finding very eccentric planets, exploring a lot of planets at the same time, like multiplanetary systems, and dealing with complicated stellar noises. And I would say that you have periodograms that deal with each of these aspects individually. Like you could have a periodogram to search for a Keplerian signal, for example, that has been done, or that are adjusting a noise model at every trial frequency, or that are exploring several frequencies at the same time. But it's kind of hard to have one which does everything at the same time. And I mean, each of them is useful in a certain context, but yeah, as Jason said, you have to be aware of the limitation of what you are using.
Vinesh, maybe you want to talk about some of the generalizations?
Well, I was just going to say that there's a well-known quote from a statistician named George Box, who said that essentially all models are wrong, but some are useful. And now I think periodograms in general, most people would agree that they're useful, but I'd like to make the maybe somewhat provocative statement that they are usually also really, really wrong, in the sense that periodograms that are most widely used in exoplanet context, like the Lomsgoggle periodogram, the underlying model is a single sinusoid plus white noise. And when you think about stellar variability, multiple planets possibly on eccentric orbits, instrumental stuff that we don't understand, whatever, a sinusoidal model is obviously wrong. And so if you have the choice, which I think probably you almost always do, to do something more sophisticated, to do a full Bayesian modeling of multiple signals simultaneously, you should do that. So I'm not a big advocate of different types of periodograms that are a little bit less wrong or whatever. But I'm also a hypocrite because I do use periodograms myself, so don't don't believe me.
Yes, I think maybe oh, sorry, go ahead.
If I may, conversely, the big machinery, the big models that we are using to model everything at the same time, they are also wrong. And well, to me, the advantage of periodogram is that it's fast and it's stable numerically. So what you see is what you get. So and the big machines are also useful, but they kind of give you a different information, a different kind of information about your data. And like, I find that when you're really not sure about what's in the data, if you have to launch a very big code for 2 days, then you look at the result and then you have to modify it and do that a couple of times to.
I guess it cuts. It cuts both ways, because if you see something, you do a preliminary analysis of your data with a periodogram, and you see something that looks really promising, but turns out to be just an artifact of, then you could be guilty of confirmation bias, and you really want to detect this planet that's not actually a planet. But maybe there's a place for both. We can agree.
The reason I use Deborah Fisher's paper as an example, and perhaps the issue with 55 Cancre-E illustrates that confirmation bias. I don't know. Is that often you have a set and you just want to know what's there, and you do this exploratory data analysis. And 55 Cancre is a pretty complex system. It even has some planet-planet interactions. But you can see all 5 planets in just a lone sparkle. And so that analysis, it very quickly lets you home in on how complicated does my model need to be? Where do I need to focus my statistics? Which of these planets require a lot of statistics and which are just so obvious? I can just subtract them off and stop worrying about them while I think about the other ones more difficult. Of course, in the end, you want to combine everything together. But I think there's a very important role for exploratory data analysis, and that's where even the lone scargle really shines.
So if I could try to summarize some of the things we've heard, there's whether you assume planets follow sinusoids or Keplerian orbits. There's whether or not you assume a maximum likelihood or a marginalized likelihood at each period. There's whether or not you assume a diagonal covariance or a more sophisticated correlated noise model. And there's something else that my handwriting is too small to read. What am I missing? Oh, multi-planets. And there's whether you search for one planet at a time or several planets at once, all when doing the periodic grid. Each of those things individually is more expensive, but maybe not that big of a deal, perhaps with the exception of doing several planets at once. But if you try to do all 4 or 5 generalizations at once every time, the expense starts to get up there. But nevertheless, you can choose based on your situation which of those approximations and generalizations makes sense for your particular problem. Okay, another question had to do with the sort of establishing the significance and how well the analytic expressions and the more computationally expensive calculations agreed. I don't know, maybe Natan, do you have some comments on when it's appropriate to use various analytic expressions and when it's more appropriate to use, say, Monte Carlo simulations or bootstraps?
So for the periodograms, my experience is that the analytic approximations are very, very good. That for the value of the FAP, especially in the range of false alarm probabilities where you would claim a detection, the analytical approximation is very close to what you would get with a numerical simulation. The question for the evidence is a little bit different, like because the evidence can be also analytically approximated, but you have like a first level of approximation, which is the Laplace approximation, and then you can even approximate it with the Bayesian information criterion. And I have no definitive answer on whether that's accurate or not in general. My experience is that usually it's reasonable, but it gives you differences in significance that are amplified. Like something that would be slightly significant with the full evidence calculation, it gets very significant with the Laplace approximation, but it's my experience, and I wouldn't say that it's always the case.
And I think this gets to another question, which was, what happens when your model's wrong? And I guess you had mentioned that the Bayesian method involves making some assumptions and explicitly specifying them. And the frequentist method may appear to be a little bit more assumption-free, but maybe that's a little misleading. So any thoughts on how well we should trust significance levels in the presence of model misspecification?
Well, as Vinesh said, all models are wrong. So my take is that when I'm analyzing a system, I'm always checking that the result holds if I change slightly my assumptions. Like, and for the priors, for example, it's true that it might seem that because you don't have priors in the periodogram, then like it's more, the result is more robust, but it goes both ways, because if something is really rare and you don't know about it, then it's something that you should take into account, because it has an effect on how you should compute the significance. But conversely, if you use a Bayesian indicator, the priors can have a huge effect, and an effect which I think is kind of underestimated, because especially on the period and the semi-amplitude, depending on how wide your prior is, it makes adding a planet more or less costly, and sometimes it varies in orders of magnitude. So yeah, the short answer is make sure that your result does not depend too much on your assumptions. That's my take.
Any other thoughts on that matter?
Well, simply that if you have enough data in a Bayesian context, your prior should become essentially irrelevant. So if your conclusions are sensitive to your prior, then you need to get more data, or you can't make any strong claims, I would suggest.
There were also some questions. Oh, go ahead.
I said that to Eric once and he got upset. I said, if you need all those fancy statistics to find the planet, you need to go get more data. No, I'd agree. And I think what really matters is how we present the data when we publish. If you know there are signals there, but there's an ambiguity in your model, is it 2 planets or is it an eccentric planet? The conservative thing to do is to not publish. But another option, which is also very good and more transparent, is to say that there's a model degeneracy here, and we don't know exactly what we're looking at, but here's model A, here's model B, here's model C. I would say if you do that, you should say which one you prefer, because people collecting these planets in like catalogs and stuff, they need you to just say what's your favorite and preferred one. And I think that's great to be honest about that, and not feel like you have to have the right answer and ignore all those degeneracies or resolve them somehow.
I think that's a good point. In the early days of exoplanets, there was sort of a big fear of making false claims. And so people tried to do things to reduce the risk of false planets, but in the process, they create other problems. And so I like the idea of our culture moving away from either it's not there, or there's a paper that says it's totally unambiguous and you can throw away half the power of your data and still find it clearly. If we could sort of be happy with papers that say, hey, there's marginal evidence, here's the best interpretation, here's 2 other possibilities that haven't been excluded. I think that would be good for open science and for improving our sort of ability to work with the data we have, rather than always just waiting 10 years for another orbit or something. There was also a question, I think probably most in reference to the GPs, but perhaps more generally about setting priors, and in particular, maybe how we choose what hyperparameters to go in to say the GP kernels, or maybe even the choice of the kernel function. And yeah, so how are we doing that? And so I guess maybe Rajpaul or Nathan?
So yeah, on how to choose a GP kernel, you do need a little bit of insight here. So there are a bunch of standard kernels, or let me say building blocks for standard kernels that allow you to encode different function properties. There's a good reference which I can maybe put on Slack. It's called the Kernel Cookbook by, I think, David Duvenode. I don't know how to pronounce his name. But anyway, you can like add and multiply, combine these kernels in various ways. But the key thing is that you need to try to think which physics do you understand, and how can you encode that into a covariance kernel. So in the stellar activity example, you know something about the time scales, about the smoothness of the signals, you know about quasi-periodicity. Those are all things you can build into a kernel. But it does take just a little bit of understanding of how kernels work. So I can suggest some references for this.
Nathan?
That's a tough one. My comment would be that I feel like the way the kernel is selected in general is a bit careless. As I said before, the kernel that you use has a huge impact on how it filters your data. And I have encountered several situations where people would use the Haywood kernel, for example, or Solidarity kernel, and just say, because the stellar rotation is this, so I use a kernel like this. And kills 3 planets. So I don't really have an answer to that problem, but I do think that there is some work to be done to find out more carefully.
Yeah, I agree entirely with you that people are maybe a little bit careless. This quasi-periodic kernel was used in RV context back in 2014, and since then that's basically the only thing people have used. That might be kind of low-hanging fruit if people want to explore the impact of different kernels that might describe similar physics. But in terms of the GP absorbing the planets, there are ways to avoid that have nothing to do with the choice of kernel. So if you use different activity-sensitive time series to constrain the GP simultaneously, so it's not as though it's the kernel's fault in that case.
But in my experience, even if you constrain the GP with other stellar activity indicators, sometimes you have still a residual effect on the periods, which still might affect some detections, especially at low frequency. But it's true that if you constrain the GP on several, or even if you train the GP on the photometry, for example, and then you use it in the RVs, but without the joint fit, then you don't have that problem.
I think this discussion was really good because it highlighted a lot of the discussion was like mathematically calculating things and getting a significance. But then you start to see here, there's more than just the number you get out. There's what you put in, and there are certainly circumstances where different reasonable choices can be made. Returning to the extraction of radial velocities, Sharon discussed the spectrum of the sun or the moon as a contamination source. When modeling that, do we have to worry that the moonlight or starlight may have bounced around and shifted or spread, or what steps are necessary in trying to model that contamination source?
So I recommend everybody to check out Arthur Roy's recent work on dealing with the solar contamination. She really has put forward several pathways in dealing with this in either algorithmically or with hardware. So to first order, they exist in the spectra, observed spectra just directly, right? So that light bouncing around your spectrograph and causing additional contaminants, I think it's more of a second order effect. I think the starlight spectra itself bouncing off and the laser frequency cone, for example, calibration sources bouncing off is more of a concern. So I think the second order term is less of a concern. And in terms of, yeah, go ahead.
No, go ahead, Sharon.
Oh, okay. In terms of dealing with it, so Avatar recommended that you have a sky fiber, which could give you an estimate of how much contaminants you have. And then perhaps you could do a CCF on the spectrum of that because that's too low signal noise to use directly. Or you can have like what NURID has. NURID is a spectrograph on the wind telescope at Cape Peak that's going to deliver better than 30 centimeter per second precision. So that has a coherent fiber bundle which measures the brightness of sky in a more precise and accurate ways than a small sky fiber that gives you a better estimate of how much skylight you're collecting.
And you mentioned that sometimes some orders had issues and were rejected. What's the process for deciding whether or not to include something but maybe de-weight it because of higher variance versus rejecting an order or other section of the spectra for being problematic?
That's a great question. So this is a sort of more of a post-processing procedure where you evaluate the radial velocities you obtained from the measurement and see how good they are. In reality, we normally have a radial velocity matrix, which is you have radial velocities through time and also as a function of wavelengths, right? So you have this velocity matrix and you can cut through slices to evaluate the quality of radial velocities at certain epoch or across certain wavelengths, say from single order. You look at the scatter of that or some sort of indicator of measurement bias, and then you can weigh them appropriately that way.
Sounds like that's another issue that there's a whole paper on. Maybe if people could post in the Slack channel suggestions
yes.
for people who want to find details about that. Okay, well, we're coming up on the end of our panel discussion.